Welcome to the course of Intelligent Product Design. In order to design an actively controllable system, we need to know that what will be the dynamic response and how do we correct the dynamic response of a system. In order to do that, one particular technique will be of high use for us, and that is what I have taken up today. That is called the root locus method. Now, in the root locus method, the fundamental idea is on the basis of the closed loop transfer function of a system. So, you imagine that this is the plant or the system that I am trying to control. The response or the dynamic behavior of the plant is what I am trying to control. So, CS here is nothing but the response of the system. So, a plant, because it is dynamic, you imagine a robot, because it is dynamic. So, its limbs are moving. So, every limb is going to create some motion, and that motion can be sensed. That is what I am sensing through the response. And this sensing that I am doing, these sensors have a transfer function Hs. On the other hand, here Gs is the plant transfer function and K is a gain. Generally, the gain is external. The gain is something through which we are giving some kind of a stimulus to the system. Now, I told you this is a closed loop system. So, this response is feeded back here, and you can see that this response is like a, you can see that this is a negative feedback system. Also, we want the system to follow a particular behavior. Okay? Suppose I am talking about a robotic limb. I want the limb to go from position A to position B. Suppose I am talking about some other system, a unmanned aerial vehicle or many other intelligent autonomous system. For every such system, we give certain commands to say that this is what will be the position now, velocity now or acceleration now. So, these are all the reference. So, this is the reference, which is what we want the system to follow, and this is the sensing. Now, a little bit of algebra if we do, what we are going to see? Okay, first of all, we are going to see that this Cs is coming here and a negative feedback is happening. So, this you can almost call it as Rs minus Cs Hs. I am just keeping it as simply R minus Ch. Now, the Kgs, because all of them are Laplace transform. So, I can do linear operation. So, Kgs times this R minus Ch is nothing but this response of the system. So, I can also write that the response that I am seeing is nothing but Kgs times Rs minus Cs Hs. So, now I can bring all the Cs in one side. So, let us try to do that. That is Cs plus Kgs Cs Hs equals to Kgs Rs, and then I can take this Cs common. So, that it will become 1 plus Kgs Hs, and that equals to Kgs Rs. In other words, if I try to find out what is the transfer function in this case is always output over input. So, which will be Cs over Rs, and that will be Kgs over 1 plus Kgs Hs, and you see that is the expression that I have told you here. Now, if I go to a little more that how do we plot such transfer functions? Let us say I first take a very simple transfer function, because transfer function will always have some polynomial in the numerator and some polynomial in the denominator. Let us say that it is going to be first order. That means, the transfer function in the numerator is going to have one root only, and transfer function in the denominator is going to have one root only, and these two roots are p 0 and z 0. Now, the root of the denominator is what I am going to tell it as the pole of a system, and the root of the numerator I am going to talk about it as the 0 of a system. So, I have one pole that I have placed here and one 0 that I have placed here. Now, if I have to evaluate the value of the transfer function at any point, okay, so S can have any positive or negative, real or imaginary or complex value, which means we are free to choose any value up to infinity all over these, which we are going to call it as a S plane. So, on the S plane, if I choose any value of S, let us say I have chosen a particular value here, which may be written here as something like, if this is the positive, let us say I call it as minus alpha plus j beta. So, this minus alpha plus j beta, I can actually put it in the transfer function. So, I can write the value of the transfer function at S equals to minus alpha plus j beta as simply minus alpha plus j beta minus z 0 divided by minus alpha plus j beta minus p 0. So, I am going to get a complex fraction, and that complex fraction I can find out the magnitude of it and the phase of it. Now, there is another way by which we can do it instead of doing this algebra. How we can do it? Well, for that this 0 and the pole marking is very much important, because the moment I put the point, I can actually draw a line from this 0 to this point, and we are going to call it as R z, which is nothing but the 0 length. And similarly, I can do this R p from the pole, and this is nothing but the pole length. I can then show that the magnitude of the transfer function will be nothing but the 0 length divided by the pole length. Okay. This is a graphical way of doing the same problem. Similarly, I can also find out T is complex. So, it has a magnitude and it has a phase. So, I can also find out the phase of T for this particular point. How do I find it out? Well, from the positive real axis, that is this positive sigma, I have to go like this, okay, counterclockwise until I get this point, and the corresponding angle is phi z. I will call it as the 0 phase. And same thing I have to do for the pole, and the corresponding angle is phi p. I will call it as the pole phase. So, this will be what phi z is on the numerator. So, it is phi z minus phi p, that will be the phase of the system. So, these are the two things that we have to always keep in our mind, and on the basis of this we will do the root locus. So, I have given you a typical example here of f s, and I have given a test point now, instead of minus alpha plus j beta, minus 3 plus j 4, and you can find out the 0 length, you can find out the 0 phase of the 0, and then the pole at the origin, you can find out the pole length, okay, and you can find out the phase. So, pole for the pole at minus 2, you can do the similar exercise, because there are 2 poles at this time. Now, the magnitude is 0 length divided by the pole length, which will be 0.217, and the total phase will be, as I told you, the 0 phase will be positive, and hence this total phase will be this positive minus this. So, it will be a negative phase in the system. So, that is the way we will calculate the phase of the system. Why I am doing it? I will tell you that just by measuring the phase of the system, we can avoid all calculation and computational complexity, and we can say whether a particular point will be part of the root locus or not, and that I am going to reveal to you in the next slide. Well, so we already know that the transfer function is kgs over 1 plus kgs hs. Now, 1 plus kgs hs equals to 0, 1 plus kgs hs equals to 0 is actually the characteristic equation of the closed loop system. This is something that we have to always keep in our mind. Okay. So, our intention is that for different values of s to figure out that what are going to be the roots of this. Okay. And we also want to know whether the point will be part of the root locus or not. That means, if I take an arbitrary value of s, I need to test it instead of actually solving this equation. If I solve this equation, I will directly get the roots, but I cannot do it. So, I cannot do it because of computational complexity. So, instead of solving this equation, for different values of the gain k, I am going to measure the phase of the system, and from that I am going to conclude whether it will be part of the root locus or not. Now, then we know that 1 plus kgs hs equals to 0. If you say gs hs is fs, you can also write it as 1 plus kfs equals to 0, which means fs will be minus 1 by k, which means if fs has a magnitude and a phase, magnitude will be 1 by k. I am not directly interested on it right now. What I am interested is the phase value should be finally coming down to minus 1, and that means the phase should be an odd multiple of 180 degree. This will be the telltale criteria of measuring whether a point is part of the root locus or not. So, this is the criteria that we are going to utilize. Let us look into an example. Okay. So, this is a transfer function s minus z I phi I equals to 1 to n. So, that means I have, let us say, n zeros and I have here n poles. Now, please keep in mind that if I call it as m zeros, then m can be less than or equals to n. M will never be greater than n. Keep this point in mind, otherwise the system will lose its causality. Now, then I get the magnitude of the system and the phase of the system exactly as I described to you. Let us now come to how do we plot the root loci. That means, with respect to the change of gain, how the position of the roots are going to change by measuring the phase. That is what we are going to talk about, certain rules that can empirically help us in order to draw the root locus. So, we have a transfer function here. It is the denominator that we have to keep in our mind, s square plus 3s plus 3, and if you solve it, you are going to get 2 complex roots and they will be conjugate roots. Okay. That means, their real part will be the same and their imaginary part will be one positive and one negative. So, now because this is a second order equation, so there will be 2 roots. So, number of root loci will be as many as the open loop poles. So, open loop poles are 2, we know that, and that means those will be the 2 root locus. And the origin of the root locus will be at the poles itself. That is the first important rule we have to keep in our mind. The second rule says that whatever will be the root locus, the roots will be always symmetric about the real axis. This is the real axis. Okay. So, this is the s plane and this is the real axis and this is where is my imaginary axis. So, you see, with respect to the real axis, the root is always symmetric, not with respect to the imaginary axis. So, now you see that in this case, symmetry always is about the root locus. So, in this case you are going to have 2 poles, and so these are the 2 poles, s square plus 4 s plus 7 and 1 0. So, whatever will happen in this side is going to happen in this side also. That is the second important point. Why this is important? That is important because imagine a situation where a pole is here, okay, and let us give some arbitrary value to this pole. Let us say it is something very arbitrary, okay. Let us say -5 plus, let us say j 3.5. The question is, what will be the other pole's position? The other pole, this distance has to be exactly the same. What if it were not there? Suppose it is here, then it will be something so that if you multiply the two, you will not get these constants as the real constants. As a result, the poles are to be always complex conjugate, so that when I multiply these two factors together, I am always going to get these constant reals and ensuring that the system is linear time invariant system. And that is what is actually telling us that there has to be symmetry about the real axis. Now, let us say that we have 2 poles here and 1 0 here. So, where the poles will terminate? Well, the finite pole, that means 2 minus 1, that is 1 pole is going to terminate at that 0 and another pole is going to go to the zeros at infinity. Let us just look into what will be the part of the real axis segment. Okay, so, real axis segment is very important because that is where we will be able to directly understand this negative clause. For example, in this particular case, you can see that you have 2 poles here and you have a 0 here. Okay. Now, how do I test that whether a point in the real axis will be part of the root locus or not? Remember, it has to be always the final angle will be odd multiple of 180 degree. Okay. So, that means if I choose this particular part, let us say, what is the angle here? Well, if I choose this particular part, and also please keep in mind that you have another 0 here. Okay. So, you have one positive 0 and one negative 0. Okay. So, that means let us start from points even beyond this 0. So, if I start from this point, so any test point, let us say I am taking a test point here. Okay. So, this is my test point, and on this test point, what is the phase contribution of the zeros and the poles? Let us look at the first 0. This 0, if I join these 2 points, this 0 is directly hitting here, and that would mean that we are going to have basically 0 phase angle here. Same thing is true for this 0, this pole and this pole, because they are all directly coming here, and you remember we always measure the phase angle from this direction real axis to wherever we are going, because this 0 is, this test point is here. So, the phase angle contribution of each one of them is 0. Now, if the phase angle contribution is 0, then it cannot be part of the root locus. Now, if I test this point, I get the phase angle contribution of this 0 is 180 degree for sure, and for this 0 it is 0, for these poles also it is 0. So, this entire region is going to have an odd multiple of 180 degree contribution from this 0. So, that means this will be part of the root locus. Same logic you apply here, you will see that this will be 360 degree here, one from this 0, another from this 0. So, 360 degree means it cannot be part of the root locus. If you come here, you will see now this plus 360 degree will have 1 minus 180 degree. So, the phase will be 180 degree, this will be part of the root locus. In a way, you can shorten up this discussion very simply by telling that root locus exists on the left of an odd number of real axis finite open loop poles and zeros, because on the left. So, suppose there is 1 0. So, left side will be part of root locus. Then there are 2 zeros counting pole and zeros together, left side will not be part of root locus. Then there are 3 of them counting pole and zeros all. So, left side will be part of the root locus. 4 0 and pole, left side is not part of the root locus. So, this is the way we can actually figure out what part of the real axis will be part of the root locus. The next important thing is the angle of the asymptotes, and here what you need to know is that asymptotes are the behavior at the infinity. Okay. So, how the poles which does not meet the zeros, how are they going to behave? If you have only one unmet pole, then you are going to get it in the left side by following this logic, which is derived from the same phase logic. Okay. So, I can find out what will be the angle of this asymptote. In this case, it is 180 degree. If there are 2 unmet poles, that means 2 poles which does not have any 0, then it will be 90 degree one, and another one is 90 plus 180, that is 270 degree. So, 90 degree and 270 degree. And then if you have another 3 of them, then you are going to look at the behavior as 60 degree for the first one, minus 60 degree for this, and 180 degree for the third one. So, this is the way the angles will be distributed to make sure that you always get the odd multiple of 180 degree. Next is the j omega axis intercept. Well, that is very simple, because I know that the characteristic equation is 1 plus kgs hs equals to 0, and all I want to know that where does it meet, if at all, cross this s equals to j omega axis. So, that can be done by simply substituting s as j omega. So, this as j omega, and then solving this equation, you are going to see where these poles are going to intercept the imaginary axis, which is very important, because that is the point from where the instability is going to appear on the system. Next is the angle checking at a test point. Suppose I am now talking about any intermediate points, not on the real axis. Suppose I take one test point. Okay. So, the test point is somewhere here from this pole. Which way I am going? Well, all I have to do is that I have to consider the contribution of phase by the zeros, poles everywhere. There are these 1 pole here, then there is this 1 0 here, 1 0 here, and another pole here. All these contributions you have to take, except the pole which is closest to it. You cannot take that contribution, because it is right there. So, if you now consider the angle contribution of all of them and do this summation, and all of these zeros positive and the poles negative, the ultimate angle will become the angle that in which the pole is going to actually make its journey. Okay. That is the way we do it, and this is the same logic that you can do for the departure angle also. And keep in mind that there can be repeated number of departures and repeated number of arrivals. In that case, we have to multiply it by r and distribute the angle between all the roots. I will now do one example. So, look at this example where I have 3 poles, one pole at 0, one pole at -2, one pole at -3. So, you have 3 pole system, and because there is no 0, that means all the poles are going to meet the zeros at infinity only. So, we have to also draw the asymptote in this case. So, let us see how we are going to do the root locus. Okay. So, now the first point is that what is the part in the root locus that will be part of the positive real axis. For that, I have to start to measure the angular contribution of each one of these poles, and that if I do, so we should be able to see that. Suppose how would it look like? Let us try to see it. So, one pole is at 0, another pole is at -2, another pole is at -3. So, this is the real part, this is S plane, this is the real of S and this is the imaginary of S. All these things you need to always demarcate. Now, if you see what part will be part of the root locus, by arguing the same way we have done earlier, this part cannot be, because it is not in the left of odd number of poles, but this part is in the left of one pole and this part is in the left of one pole. So, that means these are part of the root locus, that much we can understand. Second point is that because there are 3 unmet poles here, so we are going to get that rule that one of the asymptote will be at 180 degree and that is true, and the other 2 asymptotes angle will be 60 degree in one side and the other one will be 180 plus the same. So, this will be the asymptotes. So, that means the behavior of the poles will be that one pole from open loop pole will go like this one will go like this, then they are going to diverge and they are going to go to the right half plane, creating instability. Okay. These 2 poles will definitely create unstable situation, and the third pole will go towards the left hand side. The more it goes towards the left hand side towards the 0 at infinity, the more it will be irrelevant and the system will become a second order system, but it would become an unstable second order system. So, there are these 6 basic rules of root locus construction. First of all, n branches of root locus starts at the open loop poles and m of them meet the zeros of the same. Secondly, loci are on the real axis to the left of odd number of poles and zeros. I have shown it to you through the example. Next, for large S and K, n minus m of the root loci will be asymptotic. So, get the asymptotic angle and real intercept by using the earlier equations that I have given. Then calculate the angle of departure from the poles, that also I told you. Do not take that particular pole into consideration in the phase. The contribution by rest of the poles and zeros you have to do in order to calculate the final phase, that will give the angle of departure, and similarly for the zeros, what will be the angle of arrival, that you will do the same logic. Finally, calculate the j omega crossing using some criteria called root stability, or simply putting S equals to j omega and solving, you should be able to do it, and calculate the breakaway and break-in points using dk d sigma equals to 0. So, what are the breakaway break-in points? Well, I will just keep an example for you, that suppose I have 2 poles like this and one pole is like this. Okay. So, we already know this will be part of the root locus, and we also know that this will be part of the root locus. Now, how it will be part of the root locus? Well, these 2 poles are going to, as you will be increasing the gain, are going to take a turn and come here. After coming here, one pole is going to go to this 0, another pole is going to go towards the zeros at infinity. So, the breakaway point is, one breakaway point is this. So, this I will call it as a breakaway point. That means the point where the poles will be leaving the real axis. In fact, at that point both the poles will be exactly identical. That means repeated roots will happen to the system, and then as they are breaking away, the poles are again coming inside. So, this will be the break-in point. That is what is told there, and from breaking point then it will go one towards the 0, another towards the infinity. Now, when it is here on this branch, the dk d sigma equals to 0, because that is corresponding to the maximum gain in this point, and when it is just meeting here, dk d sigma equals to 0, because that is corresponding to the minimum gain at this point. So, this is what is the dk d sigma equals to 0 part. Using these, we can actually use this concept for engine control and various other control systems, which we will discuss in the next class. Now, this is where we are going to end today in this lecture. Thank you.